I'm also wondering, so then do the Poincare maps, I might have missed this, but do they work in like non-periodic coordinate systems?
Yeah, so the easiest introduction is this kind of introduction where there is a forced periodicity on the system, because you have an angular variable, so it has to have periodicity. But actually, the way we use them, and maybe I'm not sure we'll do it in example next week, but we certainly will do it later on, is that you can say they have a state space and you have a flow that everybody looks like they're moving this way, and then they come back after a while from some finite region of state space. Then what you do is you put what's called codimension 1 hypersurface. So for example, in the line here, we were in a plane, and codimension 1 meant an object which was 1 dimension less, which is this line on which we are mapping. But this generalizes in 3 dimension. There is a surface in which you just have to specify where you return to. So your Poincare map becomes 2-dimensional and so on. And that notion of recurrence doesn't have a periodicity built in, because different part of the fluid or different part of solar system come back at different times. It's a purely geometric notion. The state space is cut by some hypersurface and manifold. So that's a property of state space, doesn't know anything about time. And Poincare map is a very useful notion. So then what you have to do is you also have to compute return time for every point on this Poincare section, not only where you land, but how long it takes you to land. So you do not have to impose periodicity. It's much more powerful than just systems for which you have some external periodicity given to you. For me, this is the most important take home. Adjusting this heteroclinic, homoclinic things, it can be tricky, and maybe it doesn't happen. It's not a big interest. But reducing flow from differential equations to iteration, repeating a mapping, that's an amazing saving. It's very powerful. And that will carry with us.
So then for fixed point in this context, it doesn't mean a fixed point. Just to repeat, like of the differential equation, it means a point that the map
so I make
itself.
a distinction for differential equation. They're only equilibria. Equilibria are points where there is no motion infinitesimal in the time. Now maps have fixed point, which means you go 17 minutes and you come back and you're exactly where you started. So that point is a fixed point of a map. And fixed points of maps are very natural.
One thing that seems odd about this map, though, is like normally I'd expect something like that to be sort of like very discrete in the sense that it has an input and an output. But in this case, the amount of time is variable, like you were saying earlier. Like for different starting locations, it might take different amounts of time to get back. So like, how do you choose the amount of time that is, if that makes sense?
The time, actually one important thing about nonlinear dynamics is to deprogram you from your notion of time.
Okay.
So the return is a geometrical property. State space has some geometry.
Okay.
And return is a geometrical property. And the time, depends how you define your units of time, and you can non-linearly change how you define time. It won't change the geometrical property of return, or it won't change the stability of that orbit, even though you traverse it at different times. So that's an interesting thing to realize, that you don't need your clock anymore. The only important thing is, that you visit the neighborhood and that your neighbors do it in a certain way. And that's purely geometrical notion. You always start with, that's called stroboscopic map. You always start with the idea there is a disco, people are dancing, but if you flash them every 2 seconds, you see them frozen in various shapes.
Mm-hmm.
And if you know the choreography of the dance, you can interpolate between the two states, so N is before and after. So that's called stroboscopic, and it can turn out to be very difficult because different people dance at different speeds. But if you, instead of that, go to description where you say, a person is in this shape and then it's in this shape again, that means in the space of shapes, you've come back to the same shape.
Yeah.
Then how long it took you to do that is not so important. And that's the idea of Poincare sections. It really relates shapes, states, etc.
Mm.
And the return time is just one of the properties of that state. It is that long, that high, that fat, so many kilos, and it comes back in 7 minutes. Just an extra variable describing it. Here we have taken a very simple example, but usually you think of it in the following way. Your friend is a good swimmer and she's going from Banana Republic to Cuba.
Mm.
And the way she does this is she's in a shark cage and she goes through repetitive motions. There are two ways of looking at her. One is she's someplace in different places, etc. The other one is you can go through the sequence of shapes that she goes through. So she completes a breaststroke, and that breaststroke has some properties. It took so much time to complete the breaststroke. And in the process, you have translated so many feet in certain direction or so many inches. And these are just properties of the breaststroke. So a good description is just describing one period of this shape-changing thing. So in the state of shapes, you come back. And with it come all kinds of things that are consequence of it, basically. So, how long it takes is a consequence of, how it's done. And where you end up after one breaststroke also depends on how this particular sequence worked. But those are not the important thing. The important thing is that a breaststroke is repetition of breaststrokes. And if you go to the state of possible shapes of a swimmer, it's very clear and simple what it means to come back. That's a return map in that space. If you don't have that vision, then it's endlessly complicated because it's changing all the time. God knows what's going on, but it's actually just repetitive motion. So that you want to do often. You have your lab, and in your lab something is moving. But if you go to co-moving frame, the shark cage, then this is actually very simple periodic motion rather than some drifting motion. And that's what Poincare sections are doing for you. They are relating you to state to the same state, and not what it looks like in your coordinate, but what it looks like in intrinsic description of all possible states of a system. Brilliant idea. So, what Poincare did is that meant that you could go to Lagrange point. So you could change your coordinates and go to the point Moon, Earth, and Sun exactly cancels. And if I look at Lagrange point from Earth, it looks very complicated. It's doing all kinds of nonsense. But if you're there, you have extremely simple description what's going on. And you use these things to send things around the solar system. You get there and it's very little energy. You can catch a circuit in other directions and so on. So it's very powerful notion of looking at state space in kind of intrinsic coordinates rather than your lab. That's what these geometries do. It's a state space. Now, in practice, finding good Poincare section is a dark art. There's no clear prescription how to do it. Case by case, you try to do the best job.
Well, thank you. Bye.
Bye.